I made a okay, everyone. So in one of the lectures, I made a mistake. I will correct it tomorrow. I made a mistake. It's more or less a big. It's not a very big mistake, but it's still a mistake. I'll correct it tomorrow. Okay. Because now today I just need to load it fast. Now we were discussing ring homomorphisms. Let RNS. Yeah, it's recording. Let RNS be commutative rings. And phi from R to S a ring homomorphism. I mean, I'll not prove them. Phi of R, then phi of R is a subring of S. Of course, you see that? That's clear, right? Two. Oops. If X is a unit, then phi of X is a unit in Y, is a unit in S, sorry. Please, people who are talking, yeah. Okay. If J is an ideal in S, then phi inverse of J is an ideal of R containing the kernel of phi. I think that's true. So you take phi inverse as an ideal, and then yeah, it contains kernel of phi because J contains 0. Very good. 4. If phi is surjective, okay, and I is an ideal of R, and phi of I is an ideal of S, then if phi is an isomorphism, then 1 R is a field of rings, of course, here, of rings. Then R is a field if and only if S is a field. 2 R is an integral domain if and only if S is an integral domain. And then I'll leave these as exercises. They're not very bad to prove. And what as well? Let's write this down here. The group of units of R under multiplication in R is isomorphic to the group of units in S as groups. And the additive groups, well, I think that's are in the groups, and R plus is isomorphic to S plus S groups. Okay, so these are nice little problems that you can try. They're not bad. Okay, these are very clear. Okay, any questions on these or? Okay, so try to prove them. Usually it's straightforward. So the proofs are left as an exercise. Left as an exercise. Okay, but I mean you can use them, okay? You can use them in your... Okay, are we good here? Are these clear? I mean, phi will just map units to units, and the groups will be isomorphic. Yes? What does 3? The group of units of R. Did I use this notation? Yeah, I did use that, yeah? The group of units of R is isomorphic to the group of units of S under multiplication in R and under multiplication in S, and then the additive group. Yeah.
This RX?
Yeah.
So what does that say at the very end of number 3?
As groups. Okay, great. Now let's do another proposition. That's an important one. Here you have to convince yourself. I'll not prove it, but let R be a ring. And there exists a unique ring homomorphism. Phi from Z to R and phi is given by phi of n is n times 1r. Now n times 1r, I define it as is just 1r plus 1r n times, if n is strictly positive, it's 0 if n is 0, and it's minus 1, absolute value of n times, this is minus n in that case, if n is negative. Okay, now, I mean, if we think a bit about it, if you have a homomorphism from Z to another ring R, what is phi of 0? What should it be? What should phi of 0 be? 0. What should phi of 1 be? 1. What should phi of 2 be? What is 2 doing? It's 1 plus 1, right? So, now what should phi of minus 1 be? Minus 1R, okay? And then you can check that this is a ring homomorphism. Okay, it's a bit, you have technical details to check. It's not that bad to check, but just a bit long. You have to consider m and n are positive and things. If phi of mn, if m and n are positive, if one of them is negative. So it's not really bad, it's just more a tedious calculation. Now, okay, you can check that. Okay. And uniqueness, so the proof is phi. The proof that phi is a ring homomorphism is left of an exercise. And uniqueness, proof, the fact that phi is a ring homomorphism is left as an exercise. And should be additivity is obvious more or less. Multiplication is where you can have some trouble. But again, it's just obvious. Well, it's not obvious. You just have to write it down. Okay? Write it down. What I'm saying here, I'm just defining what is 3 in a ring. 3 in another ring, it could be 1 plus 1 plus 1. Right? 4 is 1 plus 1 plus 1 plus 1. Now I'm saying that 3 times 4 in Z is just 1 plus 1 plus 1 times 1 plus 1 plus 1 plus 1. Okay? It's the same thing. You just have to prove it. It's just an exercise. And uniqueness, it should be obvious. I mean, what could it be? If phi of 1, what is phi of 1? Phi of 1 must be 1. So if phi from Z to R is a ring phi, let's say phi and psi are ring homomorphisms, then they are group homomorphisms from Z to R, such that we're satisfying phi of 1 is equal to psi of 1 is equal to 1R, right? Agreed? Are we good? Yeah. It's fast? Okay. Our phi of 1 is equal to psi of 1 is equal to 1R. Now Z is cyclic, right? You agree? As a group, Z is cyclic. What is the generator for Z? 1. So once, and you have a group homomorphism. So once you know how it acts on the generator, then you know how it acts everywhere. So since Z is cyclic, and Z generated by 1, you can prove inductively and phi psi from Z to R are group homomorphisms, then and phi of 1 is equal to psi of 1, then phi of n is equal to psi of n for all n in Z, so psi is equal to psi. Okay? This is the uniqueness of phi. Great. Are we good? Yes, sir.
What is the, like, can you explain the notation phi?
If phi and psi are ring homomorphisms, then they are group homomorphisms. Okay, from Z to R. So I'm proving that you have a unique homomorphism. So I'm saying, suppose you have two homomorphisms, you show they're equal.
Oh,
Okay? Have you seen that kind of proof? Yeah, we've seen that many times, right? If you when you show uniqueness, you assume you have two of them, and then you show they're equal, right? So assume you have two ring homomorphisms, and you show that they're equal. They're equal functions. Great, awesome. Are we good? Yeah. I mean, this phi business is important. I really like it. Okay, so it's better to know it. No, I'm using the fact that it's a group homomorphism, and that the fact Z is a cyclic group generated by 1. If you have two group homomorphisms that send, so I'm using the fact that they're ring homomorphism just because phi of 1 is equal to psi of 1 is equal to 1R, right? Right? And then phi of 1 will be equal to psi of 1. Now it's they're group homomorphisms acting on a cyclic group. They're the same on the generator, so they'll be the same everywhere. Okay? Great. Now definition. This is one of the most important definitions. Well, before a definition I need to, yeah, okay, definition. Characteristic. 3. There's the definition. Let R be a ring. I mean, you don't need commutativity, but let R be a ring, and let phi from Z to R denote, or let phi denote a unique ring homomorphism from Z. I mean, I tend to say Z and Z. I don't know Anyways, what is correct? Z or Z or both are good? Both are good, right? Yeah. Depends on the country. Okay. I guess I'm from both countries because that's the Z and Z. Okay, so let R be a ring and let phi denote the unique ring homomorphism from Z to R. Then, it's a long definition. Then, the kernel of phi is equal to nz for some n bigger or equal to 2 or n equals 0. We agree or not? So we know that the kernel is an ideal of Z, right? What are the ideals of Z? These are precisely the subgroups of Z. We've shown that these are exactly the sets n times Z for some n in n. Now the kernel of this homomorphism is either 0 Z or nz for n bigger or equal to 2. It cannot be 1z because it maps 1 to 1. You see that or not? We see that? Proof. Curve phi is an ideal of Z. So there exists n in n union 0 such that curve phi is nz. We prove this, that all the ideals of Z are in the form nz. Now, curve phi is different than Z because phi maps 1 to 1, right? It doesn't send everything to 0, right? 1 doesn't belong to curve phi since phi of 1 is equal to 1r, different than 0r. So kernel, so n is different than 1. So curve phi is equal to 0 or curve phi is equal to nz for some n bigger equal to 2. Okay? Yes?
I'm not sure to understand why phi equals to 1z makes for a contradiction with it equal to 1r and not equal to 0r.
Pardon?
What does it mean?
So the kernel is nz, right? I'm just showing that n can be 1.
Yeah, but why? I don't understand.
Because phi of 1 is 1, different than 0, right?
Yeah, but of course it's different than 0, but why? What does that change? What does that mean?
It doesn't belong to the kernel. So the kernel is not everything. Right? The kernel is not everything. If you have if n is equal to 1, then the kernel is z, right?
Yes.
So the kernel is everything.
Yes.
So if 1 doesn't belong to the kernel, then the kernel is not everything. Right?
But why doesn't 1 belong to the kernel?
Because phi of 1 is equal to 1r different than 0. Right?
And the kernel must send to 0.
Exactly.
Always.
Is that clear? So what is phi? How do you check if whether an element belongs to the kernel? You take phi of that element, right? Phi of 1 is equal to 1r. So does 1 belong to the kernel?
No.
No. So the kernel is not everything. Okay? Is that clear? Yeah? Everybody, is there any questions on that? Is that clear? Okay. Great. Okay, so curve phi, we can write one else. So curve phi is different than z. So n is different than 1. So curve phi is equal to 0, or curve phi is equal to nz for some n equal to 2. Great. Now, the characteristic of R is positive integer n or non-negative, let's say the non-negative integer n. Of course it's different than 1 such that curve phi cannot have a rational, because what you're saying Z mapping to Q, if your R is Q basically.
Yeah, so 1 would be the kernel.
No. If you're mapping Z to Q, so you're sending 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 0 to 0, minus 1 to minus 1. So the kernel here would be 0.
But isn't the kernel sending to
Identity to with respect to addition. Right? Not to 1. You send it to 0. Okay? It's the same as the kernel of the group homomorphism. Okay? Is this stuff clear? Yeah? Any questions on this? Any questions? Yeah? Yes. Take Z mod NZ. That's the next. Yep. Very good. Very good. Take R, B, Z mod NZ. What is the kernel of phi? It's NZ, right? Great. We'll give you examples. Before I will try to give another property of the characteristic. Let's see if I have this written here. Sure. Okay, so example. Let R equals Z, say, and phi from Z to Z be the unique ring homomorphism. Okay. What is the kernel of phi in that case? Kernel of phi is 0, right? Because what does phi do? It just sends n. So n really phi is the identity here, right? Phi of 1 is 1, phi of 2 is 2, phi of 3 is 3, phi of 4 is 4, phi of minus 1 is minus 1. Now let's give another example. So Z, we say that Z has characteristic 0. Okay, same thing for Q. If you take phi from Z to Q, you just send 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6. So phi will be injective and the kernel will be exactly 0. Great. Now let's give another example. Let's call this one. To let R. What's your favorite number? Yeah. Pick one number. 7. Phi Z mod 7Z. Okay? Now consider the unique map from Z to R. Okay? Where does 1 go to? 1 goes to 1 mod 7. Right? 2, where does 2 go to? 2 mod 7. 7, where does 7 go to? 7 mod 7. Okay, so what is the kernel?
7Z.
7Z. Right? What is the characteristic of Z mod 7? 7. As characteristic. Okay, now, okay, could I erase this? Can I erase this? Okay. Yeah. Yeah. 0 is non-negative. Okay, can I erase this? Okay. Let's do another example. R as Z mod 4Z cross Z mod 4Z. What is the characteristic of this ring? Yeah, 4, right? So what does the homomorphism phi do? Z to R, it sends 1 to 1, 4, 1, 4. 2 to 2, 4, 2, 4, right? 3 to 3, 4, 3, 4. 4 to 4 mod, so 0, 4, 0, 4. So the kernel of phi in this case is just for z. Agree or not? Yeah? Nice characteristic. Four. Great, I'll just erase that. Okay. Now proposition. Let R be a ring of characteristic n bigger or equal to 2, then the additive order of 1R in R plus is n. This is one way to find the characteristic. You take the identity element for multiplication and you look at its additive order. So in Z mod 7, what is the multiplicative identity? 1. What is the order of 1 in Z mod 7Z? 7, right? Yeah? So the characteristic is 7. Now take R to be Z4 cross Z4. What is the identity element here? It's 1, 1 for multiplication. What is the additive order of 1, 1? How many times do you need to add 1, 1 to get 0? 4. So the characteristic is the additive order of 1R. So let's prove that. Proof. How do I prove it? Okay. First, note that if R has characteristic n, then 1R plus 1R n times. Okay, I'll just write it here. Oh man, sorry, I'll just let me write this down here. Then 1 has finite order. Then n times 1R, which is 1R plus 1R n times, which is just phi of n, is equal to 0. So 1R has finite order. Okay, now, if m is in n such that m times 1R is equal to 0R, then phi of m is equal to 0R. This implies that m belongs to the kernel of phi, which is equal to nz. Which means that hence n divides m. So what is the least positive integer that I hit 1 with, that I add 1 to itself that many times to get 0? In that case? N? Yeah. So if I add any number, if the order of m, if I add 1 m times to itself and I get 0, then m must be greater or equal to n, right? In fact, m must be divisible by n. And I know that for n this holds. I know that n times 1r is equal to 0. So I know that the order of 1r divides n, and n will divide the order of r, the order of 1r, okay? Hence, these are really group theory statements. Hence, the order of 1R, R plus, is n. Okay. Another proposition. Wait. Yeah, okay. Where is that? Let P be a prime number. And R a ring with P elements. What is the only group with P elements? It is Z mod PZ, right? The only group with P elements is Z mod PZ. Why is that? Take any group, right, with P elements, and pick a G that is not the identity. The order of G will divide P. So the order of G will be P because G is not the identity. Agree? So this means that the group is cyclic. Agree? So if I have, so my group of order P is cyclic, hence it's isomorphic to Z mod PZ, because any two cyclic groups of the same order are isomorphic. Same thing with rings. So let P a prime number and R a ring with P elements. Then R is isomorphic to Z mod PZ, and R is a field. Of course, because Z mod PZ is a field. Okay. I'm going up slightly fast because all I'm a bit fast, it's because it's groups. I'm using groups. All I'm using is groups now. Okay? And R is a field. Okay, great. Now we'll give a name for R later on. We'll call it the field with P elements. But anyways. Let's prove this. Proof. How do you want to prove it? The long way or the short way?
The short way.
The short way. Okay. Consider 1R in R plus. What is the order of 1? R is an additive group with P elements, right? R has P elements, so the order of 1R in R plus divides P. Divides the size of R, which is P. But 1R is different than 0R. Right? So what is the order of 1 in that case? The order of 1 is P, divides P, and it's not the identity element, so what is it? P, because P is prime, right? So 1R has order P. Agree? Groups. Nothing about rings yet. Nothing about rings. I know that 1R has order dividing P. I also know that 1R is not 0R, which is not the identity element of R plus with respect to addition. So 1R has order P, since P is prime. Okay. Great. Now, I bring in my homomorphism phi from the previous, the unique homomorphism from Z to R. What is the kernel of that homomorphism? It's NZ, where N is the order of 1. So it's PZ, right? Let phi denote the unique ring homomorphism from Z to R. By the previous proposition, kernel of phi is equal to PZ. Agree? Okay, now let's apply the first isomorphism theorem for rings. By the first isomorphism theorem for rings, Z modulo curve phi, which is isomorphic to Z, which is equal factor to Z mod PZ, is isomorphic to a subring of R. Agree or not? The first isomorphism theorem tells me that if I have a ring homomorphism, Z modulo the kernel is isomorphic to a subring of the codomain, right, of R. Now what is the size of R? P. What is the size of Z mod PZ? It's P. So what can I say about these two rings? They're isomorphic. Since Z mod PZ has size P and R has size P, then Z mod PZ is isomorphic to R, right? Because Z mod PZ is isomorphic to a subring of R of size P. Now R has size P, so Z mod PZ is isomorphic to R. Great. So any yes. Equal, yeah, because, yeah. Okay, now, so far so good. Great. Now, any ring with P elements is necessarily a field. So any ring with P elements is commutative, it's a field, and it's isomorphic to Z mod PZ. So we have a notation for this. We denote the field with P elements by FP. Okay? Because any ring with P elements is isomorphic to Z mod PZ, we have a notation for it that we call F sub P. Okay, so whenever I write F sub P, you can assume it's just Z mod PZ. Okay? So when I say the field with P elements, what can you assume it is? Z mod PZ. What is the field with 3 elements? Z mod 3Z. What is the field with 5 elements? Z mod 5Z. Okay? Great. What time is it?
It's 11, 12.
12, okay.
How much do
Okay.
more notation?
FP, you know, you can assume FP is Z mod PZ. Okay. Great. Now let's look at some things. Some remarks. I mean, they should be a bit obvious. Remarks. A subring of an integral domain is an integral domain. You see that or not? If S is a subring of R, if R is a domain, if R is an integral domain, if R is an integral domain and S is a subring, and A, B, R, and S such that AB is equal to 0R, then, I mean, AB are elements of R, right? Such that AB is equal to 0R. So, A is equal to 0 or B is equal to 0. Since R is a domain, is an integral domain. Domain. Blah, 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 that's good. Okay, so S is an integral. Okay, and you can prove also that if R has no zero divisor, then S has no zero divisors, because any zero divisor in S would be a zero divisor in R. Okay. Great. This is a very important theorem. Proposition. Or theorem. Okay, wait. This, well, I'll do it twice. Yes? Where? 0s? Well, 0r and 0s are the same because it's a subring of r. Okay? Is that clear? So if you put here 0s, this is still true, but 0s is equal to 0r. Okay? 0s is equal to 0. Okay? Great. I'll prove this theorem twice. I'll do it in two different versions because it's very important. Okay? So very important. So let f, suppose f is a finite field. And what? And let f be a finite field. And let phi from z to f denote the unique ring homomorphism well, of course, from z to f. Then what? Then kernel of phi is equal to pz for some prime number. So if you have a finite field and you consider this phi map, the kernel must be a prime number. Must be the ideal generated by a prime number. So think about it. Z4, is it a field? Is Z mod 4 Z a field? Let's think a bit about it. Is Z mod 4 Z a field or not? Is 4 prime? When is Z mod n Z a field? If and only if n is prime, right? So is Z mod 4 Z a field? No, it has 0 divisors. What is the kernel of this map? Of phi. It's the ideal for Z. Right? Now, try to construct any finite field. So far we know only Z mod PZ. Okay? So this is what we know for now. But if you take any finite field, try to construct one. It's a bit difficult, it's not easy. But if you have any finite field, then the kernel will precisely be PZ for some prime number. And the proof is very quick. It doesn't have to be it's not a long proof. It's an important one, so please do know it. Proof. Phi from Z to R, from Z to F, is the unique ring homomorphism from Z to F. Then, well, by the first isomorphism theorem, or you know what, let's do something else. We know that phi phi is equal to nz for some n for some n bigger or equal to 2, or n is equal to 0, right? This is the kernel. It's nz for n equal to 0, or for some n bigger or equal to 2. Now, could it be 0, by the way? If the kernel is 0, what can I say about phi? It's injective. Can you find an injective homomorphism from Z to a finite set?
No.
No. So the kernel is not 0. Okay? We'll eliminate that. And so with the first isomorphism theorem for rings, Z mod nz is isomorphic to a subring of F okay? Now F is a field, so F is an integral domain. Hence, since F is a finite field, I mean any subring of a finite thing is also finite, right? Hence, Z mod nz is a finite integral domain because any subring of an integral domain is an integral domain. So Z mod nz is an integral domain and it's finite because F is finite. So what can I say? Z mod nz is a finite integral domain. What do you know about finite integral domains? They are fields. It's a theorem we proved, right? And Z mod nz is a field, finite integral domains are fields. Now, for which n does this precisely happen? When is Z mod nz a finite field? When is Z mod nz a field? When n is prime. Hence n is p. Okay, now there's another way to see that. If I have time, I can explain it. Maybe it's more intuitive. Hence, n is equal to p. I mean, hence n is prime or n is equal to p for some prime p. We write p for psychological reasons. Okay, what time is it?
It's 22.
22. Okay, just let me just explain it in 1 second. Okay, now, what was the statement? Then the kernel of phi is pz. Okay, what is the kernel of phi? It's the additive order of 1. Okay, you agree? This is the kernel of phi. Now, suppose you have a field, and n times 1 is 0. So the additive order of 1 is 0, is n. Or the order divides n, let's say. Now, if you can factor this n, say you have 6 times 1f is equal to 0. Right? This 1f, you may be able to factor it into a product. If, say, this one is 6. Right? So if n is not prime, and this field is an integral domain, then you can always reduce it. Then this one is equal to 0, or this one is equal to 0. So if the order is not prime, you can always reduce it. So you get a contradiction. Okay? This is another way to prove it. But, yeah. Okay, do you see that argument or not? Yes? Do you see that argument? So suppose 1 has order 6, an integral domain. Right? You can write 1 plus 1 times 1 plus 1 plus 1 is equal to 0. Agree? Yeah? If 1 has order 6. Now, if this is an integral domain, this must be 0, or this must be 0. Because AB is equal to 0, imply one of those is 0. This implies that 1 has order 3, or 1 has order 2. So you contradict the fact that 1 has order 6. This is another way of doing it. Yeah?
How does permutations?
Permutations? Oh, 6 is a 6. Yeah, 6. Okay, 6. Okay? Any questions? Great, so please this up. What time is it? 24. Okay, should I discuss one homework problems or I have like 5 minutes. I can discuss it. I didn't do it yesterday. Do you want me to do it or not? It's the one on S4 and S3. Do you want me to do it? Okay. So there was a problem in the homework. So it started by show that S4 has a subgroup of order 8. Okay, find the subgroup. Okay, I'll do it verbally. Find the subgroup of order 8 in S4 and show it's not normal. It's not normal in S4. Okay, and I ask you to list the elements completely, right? That's what I asked you. Now, how do you find a subgroup of order 8 in S4? Don't go by brute force. Don't go try to construct one. Yeah. D4. What is how do you want to represent it? Yeah, but I mean, how many copies of D4 can you find in S4? Maybe you can find more than one. Right. Exactly. So how do you want to do it? You want to pick a square, right? 1, 2, 3, 4. Very good. So 1, 2, 3, 4. So if you want to find a group, it's just the group of symmetries of this one. So you take the identity, you take a cycle 1, 2, 3, 4, then the square of that, which is 1, 3, 2, 4, and then 1, 4, 3, 2. Then you have the vertical reflection. What is it? This is 1, 2, 3, 4. Then you have the horizontal reflection is 1, 4, 2, 3. And then what as well? You have the two diagonals 1, 3, and 2, 4. Okay? So this is a subgroup of order 8. Now why is it not normal? There are many ways to do that. But let's try to just pick an element, conjugate it, and see that I don't land in H, right? So pick an element that's not in H. In this case it will work. Let's say 1, 2 times 1, 3 times 1, 2. What is that equal to? This sends 1 to 2. 2 is fixed and 2 to 1. So it's fixed. So 2 is sent to 1. 1 is sent to 3 and 3 is sent. This is 2, 3, right? And that doesn't belong to it. So H is not normal in S4. Okay? Agree? So far so good? Yeah? So far so good. Now, I ask you then to find all subgroups of order 8 in S4. How to do this? The idea is that 24 is 2 cubed times 3. So any subgroup of S4, what time is it? 27. Of order 8 is a CeLO2 subgroup. So the number n2 of such subgroups, so I'll go a bit fast. I will not define by notation. So the number, I'll use the notation in the lectures. So the number n2 of such subgroups is 1 or 3. Because n2 is congruent to 1 mod 2, and n2 divides 3. Now if n2 is equal to 1, then H would be normal. But hence H is not normal. So hence n2 is equal to 3. Then I ask you to find all the subgroups of order 3, of order 8 in S4. You have 3 of them. You have H, and how do you find the 2 others? Don't conjugate them. If you conjugate them, you will, it will take you some time. What's a good way of finding them? Just relabel your square. So we had a square 1, 2, 3, 4. And then relabel it. So let's say 1, 4, 2, 3. And then we can do one more. What is it? 1, 3, 4, 2. 1, 3, yeah. Okay? Write down the symmetries of these. 1, 3, 4, 2. Write down the symmetries of these, and you get that you have 3 subgroups of order 8. Okay, now for the last question. Is it clear or not? Yeah. Now for the last question, I ask you to find a surjective ring homomorphism from S4 to S3 using this. Now pick your coset, pick your subgroup H, and consider the homomorphism from S4 to S3 induced by the action of S4 on the cosets of S4 mod H. Many ways of doing that. Now, you know that the kernel is the intersection of these 3 subgroups. Now, look at the intersection of these 3 subgroups. What is the intersection? What do you find the intersection is? What is the intersection? It's a normal subgroup of size 4 in S4. What is the only normal subgroup of size 4 in S4? This is just 1, 1, 2, 3, 4, 1, 4, 2, 3, and 1, 3, 2, 4. Okay? And then S4 mod that will be isomorphic to, what is the size of S4 mod that? It will be 6. So by the first isomorphism theorem, it will be isomorphic to S3. Okay? Wait. Oops.